Good afternoon, everyone, and welcome to our research group, to the honor students who are undertaking their research projects for their final year. So for today, we're going to be presented by Prof. Frandir, and his talk is on looking into the integration of fundamental models, looking at machine learning models and the optimization or rather operations research. Now, this is something that he thought quite relevant to all of us, such that as we learn to apply these things to improve in terms of our coding for machine learning models, and also that we can have much more improvement in terms of very robust predictors or classifiers. So I'll hand over to Prof. And he can take us through the presentation.
Great, thanks very much, Emmanuel. And maybe to motivate the presentation, it's also that in the group, there have been a number of different questions coming from different people and some subtle errors creeping in, where sometimes someone's work, which is in a particular area, there's a little bit of confusion about how the other parts relate to it. So I've tried to produce a map that helps clarify some of that. And then, of course, with the people in the group new to machine learning and needing to understand the difference between that and the standard type of modeling, where we have more like continuous type variables, then this presentation should cover that. We have had that presentation before, but I think in terms of the number of new people in this field, so there is some overlap with that earlier presentation as well. So without further ado, this slide is just explaining the difference between the, it says fundamental type models versus the machine learning models, but it's not exactly about fundamental versus machine learning. It's more about the difference between predictive type models and classification type models, right? So that's one difference. The other difference is about the fact that one is fundamentally derived. And when we say fundamentally, we typically mean that in terms of our understanding. So based on our understanding of the physics of a problem, we propose the model and hence the associated mathematical form, and we solve it. So that one is very much based on what we understand and the current state of physics and so on. Whereas in machine learning, we already have a kind of pre-baked model. In fact, in machine learning, they hardly think about the model because that's already a pre-made thing. For example, neural networks, you've got basically layers of neural networks, and you talk about the architecture of the network, but it's not really a model in the sense that it's something that represents our understanding. So fundamental models proceeding from our understanding versus machine models, and it should say machine models, not machine learning models, but the machine model where there's a preset mathematical structure and we are simply fitting the parameters around that. So there are two types of differences, right? One, understanding, one, whether or not you are using understanding, and the other one in terms of whether it's classification or prediction. And the fundamental models tend to be the prediction type models. You are trying to predict some value. So you are, for example, you are trying to predict what the temperature will be in the reactor. And we know temperature is a continuous variable, right? It's not discrete. It's not the case that temperature can only ever be 100 degrees, 200 degrees, 300 degrees. Any value in between or around, that's possible. So that's the classical model that in a way we have a bias towards as engineers. That's pretty much the model that we default to. So we are familiar with models of this form. So we are trying to predict some output, and we have some input values and some set of parameters. And so that's our standard model. And we are typically trying to fit the data that's available. We are trying to fit this model to the available data, and we do that by adjusting the parameters. So we usually accept we know X and then we don't know P, so we vary P. until we get the model giving us the same value as the data that we've got. So that's what we are all familiar with. On the other hand, in machine learning, the situation is different because your output value, right? And by the way, here we are talking about supervised machine learning, right? There are other types of machine learning, but for now we are talking about supervised machine learning. So in so-called supervised machine learning, your output variable, we actually call it a label. And there are only so many labels. So it's quite often the case, your output is discrete. And as I said, it's often binary. It's yes or no, true or false. So for example, if you think about creating a machine learning model, which will predict whether someone will pass a course, right? Then your output variable is yes or no, will pass or no, not pass. Okay, so it's a binary output, right? And so here we are talking about classifying a set. So if we have a set of students, then we want to classify them. We can say, according to the inputs, it looks like this student is on track to pass, or this student is going to fail. So that's classification. It's not exactly prediction. If we were to apply this classification to the same example, you can try to predict what result a student will get, right? So it is possible in that example to imagine both prediction and classification. And that does raise that perhaps classification, it can be simulated almost as a discretization of prediction. So if you predict marks, and then you just discretize it into 0 to 50 and 50 to 100, right? If you just create those two classes, then you've translated a prediction problem into a classification problem, right? So in that case, you could do it. Not all problems can have that easy translation, but that one does. And so if in machine learning, we are more concerned with classifying a set, then what also happens is that we are often concerned about how accurately each label is. So when we say that a certain group of students is likely to pass, then we have a certain accuracy around that. So maybe the accuracy for students passing is 70%. And then the accuracy of our model for students who fail, that might be something different. It might only be 40%. So you can talk about, in a machine learning model, we have different states, right? It's the same variable. There's one variable out here, it's 0 or 1. But we can talk about different accuracies. So for 0, there's a certain accuracy at which we can say, yes, it's 0. And then for the 1, there's a certain accuracy with which we can say, yes, it's a 1. And again, there is an analogy with the continuous variable case. And we don't think of it that often, right? If we go back to this case where we are fitting data to a model, we typically look at one index, one accuracy. So we talk about an R² value of our fitting. So we say, okay, so let's look at these this blue line and these blue dots. So we've got all these blue dots, and then we fit this blue line to it. And then, okay, we say there's an R² value, there's a Pearson R value of 0.95. Right, and so we are in effect giving one accuracy to the entire fit, but that is a choice, and we don't have to do it that way. We could say instead, what's the accuracy of my fit for all points above 5,000 here? So only if I look at the values up here, I can calculate an accuracy of these points. And that accuracy will be different to the accuracy that we get for the points down here. So even in the continuous case, this idea that your accuracy of fit can be different for different ranges of values, it applies there as well. So we just don't default to it. We often don't emphasize one value over another. Quite often when we are dealing with fundamental models or continuous variable models, we are happy with just one accuracy value. But it does exist. It is possible to do it, to look at accuracy in different regions. And in fact, it's not done for a good reason when we only use one value, because it's often the case in engineering, certain ranges are more important than certain other ranges. So, so this notion of different accuracies in different regions, that is an easily observed feature in machine learning, but it's also easily observed in the continuous case. So that's a kind of starting point, because you'll see the strange, it feels a bit strange when you get into machine learning. You know, why now do we have this false positive and false negative and true positive and true negative? It's because of that, right? Sometimes it matters more to get this classification right than this one. And we'll see some examples of that. And so I've tried there to show some parallels with the space we are coming from. So everything we learned in the undergrad degree, it's practically all been about fundamental models and about continuous variable models. In machine learning, what I want to emphasize here is it's not an entirely different field. It's not the case that you now have to throw away everything you've learned in the first 4 years of your study. With a short step, you can bridge the gap between fundamental or continuous models and machine learning models, right? So that's there. And now for the people who saw that part before, we are now looking at we are looking at trying to understand the different pieces involved in the whole enterprise of process modeling and optimization.
Having taken care of.
Right. So here I'm trying to show in our group, we have various people working on different, are concentrating in different areas of study. And this is where I say some people are not so clear about what they are doing relates to the other things. So I tried with this map to show this, and we're just going to move this. Yeah. Okay, so running along this blue thread basically shows most of the activities. And then these other blocks here, the green and red and gray, those are more the flow of data around that. So first, we look at collecting our original data set, and quite often we'll have that available as a table. So you'll have a table, rows and columns, and I'm not saying matrix, because a table, it might be the units are different among the different columns. So if we are talking about a supervised problem, so you typically have some output column. So there's some column of Y values, and then you have some input columns as well. And I'm actually going to use the Hydro Blue. So one of the projects here, I'm just going to remove this. So here we've got latitude and longitude, and we've got the whether when you drill a borehole at that location, whether you get an active borehole or not. So 0, it's not a good borehole. 1 is a good borehole if you drill at this geolocation, right? So this is a table of values, and if you look at it, it's very hard to make a good model out of this, right? Because you've only got geolocation here, and now you've got whether or not a borehole was active. And you see whether a borehole became active, we understand to be dependent on several things. So it might depend on how much rainfall there is in the region. It might depend on the geometry below the ground, so the presence of aquifers, many other factors that that affect how good that borehole is going to be. It will depend on the mineral deposits in the rock formations and all kinds of things like that. So our original data set doesn't seem to have any of that data. And so we have a data set to begin with, but it's not so useful for creating a model. And that's typically the case, right? It's quite often the case that you'll get a data set, but the data that's in that data set doesn't get you all the way to, before you even talk about creating a model, you might not have enough in that data set to even begin thinking about creating a model. So what do we do in a case like that? Well, what you can look at doing is supplementing that data set. So you can look at, can I get more data about those? So we are still talking about the same data set to begin with. So we've got these geolocations and we have our output variable. So this is useful still, but what we want to do is add more data about the things that we think actually affect this outcome. So what we can do is connect that to another data source. And that's what we did in this case. We connected to the Google Earth engine. And using that, we are able to get vegetation index. And you can see here things like the dew point temperature, evaporation rate, soil type, and so on. So this is, if you like, a second activity that we tend to do. We tend to look for APIs, application programming interfaces, so computing systems that we can query and we can ask for more data to help us supplement our data set. So we started out with this data set. We have an output, that active column, and then we have two inputs, latitude and longitude. And we said that's not enough. Those types of inputs won't really help us to correlate our borehole activity. So what we want to do now is supplement with some data, which we happen to get from an API. In this case, it's the Google Earth engine. And now we can get more input values. So now we've got all these other input variables. And now we have some hope of correlating this. And in fact, what we would typically do is just throw away these two columns. We don't expect to use the actual geolocation as a thing that affects whether or not our borehole will be active, right? This is in effect just a way to cross-reference the variables that actually matter, right? These variables matter because they tell us about the environment of that borehole. So once we've got all this, we don't need these anymore because this is not part of our model. Okay. So now we have some columns which we expect to give us a much better correlation with the output. The next question is then, how do we create that model? So at the moment, we just have a data set. So to create the model, we can start with our fundamental model. So in this framework, I'm suggesting that we start with the fundamental model. And you see, not everybody does this. It's quite possible. And in fact, most people don't do this. Most people jump straight here to the machine model, right? And in our group also, the people who are focusing on machine learning, they will jump straight to the machine model. So what I'm suggesting here, sorry, let's see something in here. Okay. So what I'm suggesting here is that we first create a fundamental model, right? So we propose something about, so looking at the data we've collected and the value we are trying to predict, we think about, are there relationships? So for example, can we look at the vegetation index? Do we expect, or do we have already a model? It might well be in the literature that there's someone who's worked out this is the relationship between the vegetation index and the activity of the borehole. So we can propose a fundamental model there. And then that model we can say I've used F for fundamental. So we have some kind of fundamental model. So we go through a modeling exercise, and of course that involves fitting parameters and all of that. And so eventually what you have is a mathematical model which will predict certain output values for you. So we've got some output values predicted by our model, and then we can say the actual values that we've collected in terms of the data. So this is actually the data here. So the actual value of y will be the value predicted by our fundamental model plus some residual. So there's some leftover piece, some offset from what the model says, because we don't expect the fundamental model to be 100% accurate. It will be based on certain assumptions, and then in places where those assumptions are not so good, the prediction won't be so good. So there will be some error or some residual that's left over from there being a difference between these two. So that's the residual. And in this framework, excuse me, in this framework, I'm suggesting that the machine model is what we use to correlate the residual. So to me, that is the best way to position your machine model. It helps you find the residual. It helps you account for the residual that your fundamental model cannot account for. And so by adding together your machine learning model and your fundamental model, you have hopefully a reduced error. So you still have, so generally speaking, you still have a residual, but it is hopefully smaller than the original residual, right? The original residual was what's left over directly from your fundamental model. Now you have a residual that's left over from your fundamental and your machine learning models, right? So that's, that to me is a useful way of still taking advantage of our knowledge in fundamental model development. Because it might seem strange to you, there's all this hype around machine learning today, and where does that leave us in terms of the years we've put in terms of developing reactor models and understanding residence time distribution and all those good things. So this is how we can integrate the two together, right? So we can develop a machine learning model, and so we have this, and it can be in this framework, we can use it purely for the residual. Then I've also recently had some questions around, I'm in more optimization, so how does machine learning fit into that? So I would say optimization is not directly in machine learning. To me, the default tool set that we are looking at is operations research. So the people in the group more involved in operations research, they are looking more at optimization of a process. So they've got some system and they want to know, for example, how do we best connect the industries that are consuming a certain chemical and the industries that are producing it. So creating that matching, that's an optimization. So there is optimization, and it's largely based on operations research, at least in our group. And the way that we connect that in this framework is by defining for ourselves an optimality criterion. So we need to know what it is we are trying to optimize, right? There's no such thing as optimization if you don't know what you are trying to maximize or minimize. And quite often we default to the simplest thing, right? Money. So in engineering, by the end of the day, there's some commercial outcome. So we want to maximize the profit or minimize the cost. So, so that is the basis of an optimality criterion. But to define that as a quantity, we need some prediction of the process, of what the process is going to do. So we want to search among all the possibilities. So we know that in our process, we have all these inputs, and some of those we can choose and some of those we can't. But if we can choose some values of our inputs, so for example, we want to blast a certain flow rate into that reactor. So we want to know what's the best flow rate to use for me to maximize my profitability from this reactor. So what we need to know then is the implication of changing that flow rate. So how will that change how the system performs? So now we have a model for that. So that's the whole point of this modeling exercise. We can predict how the system will respond when we apply an input. And then given those two things, we should be able to calculate a value for the optimality criterion. So the criterion is just a relationship. And it's not trivial to find that, but we also need to get a number for it. So this criterion might be some rule that if your value is this and if your inputs are this and your output is that, or in other words, if your state variables of the process are this, then your cost will be that. So we use the model to search the space. We try out different values for the inputs and we get different outputs, and then we can use the criterion. And then that tells us a number. So once we have that set up, then we can use our optimization to efficiently search the space. And then that will give us a recommendation. And that can be a single recommendation to say how we should operate normally, or it could be a recommendation that's updated every few seconds or every second or every sub-second. So it could be a control system. That's what I'm trying to say there. So that's how it all fits together. So in the group, some people, I'm looking at you, Emmanuel, working on control systems, Pilani as well, looking at how do we detect for the onset of failures, and how do we then avoid that? So that's more like a control problem. So that to me sits out here. And then quite often we are developing a model, and we could jump straight to the machine learning versions, but we could also go through a fundamental model if we understand the process well enough. And then that gives us a better model. Okay, and maybe just pause there for a second. Any questions or comments there so far? Okay, so just to see if I've covered all the points here. So we've said this. So when we're not just throwing away our understanding, this is how we can integrate fundamental models and machine learning to capture the residual. And what this almost implies to us is a way to improve our understanding of the process. So you see, if you are using a framework like this, maybe you start with just jumping straight to the machine learning model. And then while you are doing machine learning, you notice, well, it's not surprising. I do see an exponential relationship between my rate of reaction and my temperature. So then you realize, yes, it does fit an Arrhenius relationship. So let me go back here, and instead of jumping straight over fundamental models, let's put in first an Arrhenius model to predict the reactor's performance. And then that will capture quite a lot of the variance, leaving you with a smaller residual. And then you use the machine learning model, and then it might be after a bit more time, you realize, okay, it seems to be that there is this variable that in particular, let's say concentration, is now catching most of my residual. So let me go back to my fundamental model. Maybe if I look at improving my rate expression, then I capture even more and I have a smaller residual here. So in other words, by trying to reduce the residuals here and shifting more of the load onto the fundamental model side, you slowly develop a complete understanding of that process. And in fact, you could say that this has always been happening naturally in science and engineering, right? When the first engineers and scientists started, let's say the engineers, when they first needed to produce polymer, it all happened by accident. They noticed in the oven when we leave trace amounts of chlorine, then somehow we get this extra polymer. So they were jumping straight to the observation. So a very empirical way of doing things. And now you have a way of iterating that so that you cycle back more of your understanding into your fundamental model until you eventually have quite a large amount of data captured by that step. There are some issues around that. So you have to look at also the computational expense of evaluating these models. So machine learning models, especially with all the libraries that support them today, tend to solve quite quickly, whereas some fundamental models, it depends on the mathematical framework, some can solve quite slowly. So for example, if you have a very fundamental model based on Navier-Stokes equations, then you have to solve 3D unsteady state fluid flow equations. It's very fundamental, you understand everything very well, but it probably solves too slowly to be of practical use. So for computational reasons, you might actually elect to stay more empirical and more machine-like. So that's the other optimization that you have to pay attention to. Okay, so I hope this picture helps if you are having any issues placing where your work concentrates. Maybe any questions or comments there so far? Okay, then moving on, looking at, now we've promised that you've got this way of connecting these continuous models and these discrete models. So let's look at the two main cases. So for prediction purposes, right, it's straightforward in terms of fundamental models. Your fundamental models are mainly continuous models, so they don't have any problem just directly predicting a variable. But if you want to use them in conjunction with the machine learning model, and if this output is, let's say, binary or something like that, then there's a bit more work to do. So number one, you can look at the contribution by the machine model as being discretized. So you could take the output variable and you could define a certain number of discrete states, and you can look at predicting which discrete class it falls into. And then for that class, that's its contribution to the prediction. So that's one approach. Another one is if you are familiar with boosting in machine learning, you can actually estimate a probability of being in a certain class. And then you can use that probability together with the value of that class. And then that gives you a continuous variable. So here I'm waving my hands through this a little bit. It's not so straightforward, but that is how you can get machine learning models to contribute continuous variables so that when you add them to your fundamental model output, you get a prediction. On the other side of it, in terms of classification, your fundamental models, you could, of course, simply discretize the output. So like that example with the pass-fail. So if your fundamental model is actually predicting your mark, so if it's predicting 70%, then that's a part. So you simply discretize the output from a fundamental or from a continuous model. You just discretize it, and then you've got the discretization from the machine learning model. And then you look at if you have some measure of the accuracy of both of those, then you combine the two, and then you estimate the probability, because if they are in conflict, then there's a bit of work to do to actually figure out which one is pointing which way. So for the two types of model and the two types of contributors to the model, that's how you can combine them. Okay. Then the other thing to think about is, yes, that's how we can integrate their outputs, but there are useful things in machine learning that can actually help you in your fundamental model development as well. So the way I'm looking at this and the way I'm presenting it, it's more that fundamental models are better, and machine learning models take care of the residual. But we should revisit that, because you can learn a lot about your process using machine learning methods. So so developing a fundamental model is not a straightforward thing, right? It's not always the case that you have a big, well-developed theoretical framework that you can just modify to your context. So quite often you have to spend a lot of time analyzing the data, understanding the influences that you are seeing, interpreting them. And you can use traditional machine learning methods to accelerate that process. So things like Pearson R coefficients to understand the sensitivity of outputs to the inputs. Those are all standard things in machine learning. Singular value decomposition to look at the best combinations of your variables, the linear combination of your variables. What are the eigen features of a process that we need to incorporate in a fundamental model? And even basic regression, even multilinear regression, you can go very far with that. Even if it's not a fundamental model, even if it's just an empirical model. So not a machine learning model, but if you have a regression model, right? And that's something I didn't spend enough time saying, that we are saying here fundamental models and then machine learning models, but also sort of next to fundamental models, you can also just have empirical models where you just fit something, right? So fitting, it's not quite the same as your machine learning. It's still a continuous variable fitting, but that's another important way to improve your accuracy. Okay, so that's the fact that we can use machine learning to accelerate our fundamental model development. Then some case studies here just to illustrate this machine learning flavor about that particular states matter. So in this example of predicting whether a student is at risk of failure, we recognize here that one of those states is more important to get right. So let's say our reason for developing this model was we wanted to direct students for counseling. So let's say we were senior executives at an education institution, and we want to counsel the right students. Now, if we get it wrong and we classify the students incorrectly, let's say we predict the student is going to fail when they were going to pass, right? Then we are doing extra counseling of a student who was going to pass anyway, because we thought that student was going to fail. In a way, that doesn't matter so much. It just means we've sent a student for some extra counseling, and maybe that extra counseling had helped that student to do even better. So perhaps we've a little bit wasted the student's time, and we've a little bit wasted our resource of a counselor, but still it has overall a reasonably good outcome. On the other hand, if the student, if we thought that student was going to pass when they go on to fail, then we've missed an opportunity for important counseling that could have helped that student avoid failure. So that's a much worse consequence. So it matters to us where the accuracy sits. It is more important for us to correctly classify students who are going to fail. So that is an example of where the classification matters more for a particular label, right? So remember, output variables in machine learning, we call the values of those output variables labels. So that's one example. In terms of that borehole example I showed earlier, so if you misclassify a borehole, and then you end up drilling where you shouldn't drill, and that has environmental consequences and serious cost implications. And then if you don't drill where there was good water, then that can even affect the socio-economic activity of the region. So there are different consequences, and probably the right thing to do is evaluate the economic impact in either case. And economic doesn't only have to mean money. Like in the first example, it can mean time, the amount of time or the amount of your counseling resource. Sorry about that. Then the third example there, just a toy example. If you look at beach sand prospecting, so every now and then you see someone walking along on the shore with this little metal detector, and then they find probably mainly keys, but sometimes you might find rings, or, valuable rings and things like that. So a beach sand prospecting. So if your metal detector goes off incorrectly, all you've lost is maybe a few seconds of stopping to pick up whatever it was. Again, that has different consequences in terms of being right and being wrong. Okay, so those are some case studies there. And so we represent that as true positives and true negatives. So if it is true that something is positive, so let me back up. So let's say our problem is to classify whether something is positive or negative. And then we want to know eventually, was it true for me to classify it as positive? So we want to be here and we want to be here, right? We want to know if it was negative, is it true that it was negative? So, for example, if we say the student is going to fail, right? Then we are unfortunately we're calling that positive. So if it's true that the student did fail, so that is a true positive. And then if the student is going to pass, is it so? Did we get it right? So we want to be on this diagonal here, and then if we say positive, that student is going to fail, and it's a false, then that means that one has a different consequence compared with here. When we say no, we don't think that student's going to fail, but it's false and they do go on to fail, then we might miss an opportunity for counseling. So we use the so-called confusion matrix to keep track of all these things. So typically we'll have our prediction. So our model will say these students will pass and these students will fail. And then we'll have, after the results come out, we'll be able to tell whether or not that was true. Right. And here I've got an example with some numbers, and this is a real case where we were trying to fit the right values. And the whole point of this is that the measures we use are not always the right measures. So if we take a simple accuracy-based approach, right? So for our default might be to say, well, let's just look at all the times we got it right and then all the times we got it wrong. So we know we like to be here. We like to correctly classify passes and correctly classify fails. So 33 plus 17, and then divided by the total number, and then divided by the total number here of all the students. So if we add up all the numbers in all these cells, then we find our accuracy is something like 68%. Which is sort of okay. For real world problems, 70% accuracy is fairly good. But in terms of our actual application, where it is more important for us to correctly classify students who are going to fail, it's actually not so good. Because you see here, these are students that we thought would pass, but then they failed. So we didn't counsel these students. And then here we got it right. These are students we thought were going to fail and did fail. So here, these are the two most important numbers to look at. The fact that these students passed and we knew they were going to pass, that doesn't matter in terms of our actual application trying to figure out who should we counsel. So this is what really matters, these two groups of students. And 15 divided by 15 plus 17, that's, well, that's actually less than, I'm not sure why it says 53%. I may have mixed up the true and false here, but it's on the order of about 50%. So actually, the important accuracy to us is not this 70%, it's more like 50%. So that's why it matters that we understand our problem well and that we use the correct measure to benchmark our fitting. So when we develop the model, there'll be some index that we try to minimize. So this is showing, in this case, accuracy is not the right metric to use. What matters is the so-called recall. And so in the case of classification in machine learning, when you are trying to assign the correct label, we have to look at the measure, and we have to understand the measure in the context of the problem we are trying to solve. So that's why machine learning needs more care. That's also why there are lots of issues today with people applying machine learning incorrectly. This is part of why in business, in the industry, people are complaining machine learning is not having the right outcome. And that's because quite often you've got someone who's just downloaded a bunch of Python libraries and gone and run fitting. Oh, the accuracy looks great. So you have to look at the problem, look at the thing you are actually trying to solve, and then use the correct measure to do your machine learning well. Okay. And this is giving us some other more general methods. So the so-called ROC curves, receiver operating characteristic curves. So this also gives us a good measure. We want to be here. This is the best place for us to sit. This gives us a kind of a balanced look across our indices. So if you really don't understand the problem well enough, with the ROC curve, you can say, okay, the model that helps me get the closest to this point is likely to be the best one. So if you can't get a good understanding, or if it's so much of a black box that you can't make good decisions, then ROC curves give you a good indicator. And that's basically it. So I have covered what we did before about the different, about the confusion matrix. And to me, what's really new now is about this kind of framework for looking at how to complement what we do in fundamental modeling and machine modeling. Thank you.
Thank you, Prof, for that presentation. At this moment, I'll open up the platform for any questions that could arise. Any questions?
Right, okay.
Yes, go on, Josh.
Okay, so Prof, I think on the slide when you came back the second time, you alluded a bit towards the regression models. And I know that previously I had tried them. And this was just my observation, and it might be something unique to me, or I don't know if it's something that is associated with regression. That's what I wanted to find out. But I found that with the regression model, I required a lot more data points when I was trying to actually do the machine learning. So when I had developed the first model, and just for those who are new here, so I was working on a model to try to estimate the drill depth of a borehole site. And I found that when I tried to do regression, although it had certain accuracy rates and stuff, when I actually tested the model, it was only as I started added in like exorbitant amounts of data that I was actually getting a better result. But with classification, I didn't seem to have that problem. So my question is it is it the case that with regression, it generally does require more data than with classification?
Thanks for that, Josh. It depends on how you did it also. In the regression, if you used multilinear regression, then there's just one solution. It's not the case that it's a search, right? In multilinear regression, there only exists one best fit. When you apply it, you will get the global best. It's not that you have to settle for local minima. So if it was linear regression you were doing, that's the best you could do. Then comparing that with machine learning, you see machine learning, if you are, again, it depends on your environment and how what your setup looks like, but you were probably using scikit-learn or something like that. And in that case, it will do a pretty good job, right? Those algorithms, that library has been developed umpteen times with thousands of contributors. So probably the machine learning one is highly developed. And in fact, you can actually adapt your linear regression to be a machine learning classifier as well. So if you do your linear regression and then you just set some cutoff and say below this value, it's classified this way and above this value. So the point is, it could just be yet another machine learning algorithm. And then, you've got boosting on top of machine learning. So you can really get high accuracy with machine learning with the problem of possibly overfitting the data. So you've got a very good chance of fitting well with machine learning. And then regression, it's almost like comparing, one little sliver of something with this massive library of this massive arsenal. So in a way, it's not that surprising, right? It also depends on the data and the amount of variance in the data and how closely that data fits with the implied model. So among all these machine learning methods, there is a model, there is something that's saying, I believe the data is sitting this way or that way. So if your data sits better with one of the other algorithms other than what your regression method was, then that will happen. So it might be a feature of that data, but also generally the machine learning itself is very well developed. And that's why we are also looking at doing it like this, right? Because a purist could say, look, I only work from my understanding. I'm only ever going to do fundamental models. I don't care about these commercial people with their machine learning. So, and I was that way in my younger days, I can say. But today, the machine learning, it's so powerful that this hybrid method, I think, will give you overall a better approach.
Thanks for that, Prof. It's interesting.
Yeah, sometimes we don't take a step back to look at how to stick it all together.
Any other question? If there's none, then maybe we can comment on the overall impression of the presentation.
Hi, Emmanuel. I have comment on that. Prof, I really enjoyed today's presentation because it did help connect the dots. Like just starting and getting my journey going with machine learning and stuff, it helped to really see the flow of how things connect. So in terms of the presentation, I think it was really needed for the start of my stuff. And please upload the recording of it.
Sure, I'll do the upload. Maybe also for people a bit newer to the group, in this part, you also, if you're saying something positive, you also have to say something negative about the presentation, because this is the section where we actually learn how to improve our presentation skills. We all always need better presentation skills. So over to you, Subhashan.
Can't think of a critique at the moment. In time, when I get used to it. Thank you, Emmanuel.
Yeah, on my end, I just can say I like especially the comment on the confusion matrix, which I think is one very important thing as people who are dealing with machine learning to understand, because many times we get too excited and run away having a high accuracy, but yet in terms of looking at the cost of how you can falsely identify something, and that can have some serious consequences at times. So to be able to understand what is the implication and not just to be focused on the accuracy, while the accuracy is an interesting value to look at, but to have an impression of the overall consequence of falsely identifying something. So, well, I wouldn't say this is a critique, but I don't know if at the level of the undergrads, if the examples that were used to their comprehension, well, I don't think they're maybe per se at my level any too deep, but I'm just saying I don't know if at their level maybe Salvation or anyone can say they comprehend the examples that we used, if they were clear enough in terms of explaining the concept in terms of the consequence, what it means, the 3 different examples that we used.
I can definitely answer that. Yes, it was comprehensible. The counseling example is good. From my experience, I was in that position at some point in my degree. So, but then I like to say I was skew in the data set, because as much as I was in that point, I always pushed to pass and do well. So I had low marks at times, but I still passed. But you know, it is understandable. And then with the borehole example, like I'm sure most of the guys are doing their research proposal, or they did give it in, and they would have picked up, like, you know, the type of features they need to investigate for their projects. Like the borehole, while it is specific to geoashes, like the leaf area index, the precipitation, all these features and stuff is relatable to my project and stuff for the tracking stuff. So it definitely was relatable.
Okay, that's great. Yeah. Any other comment? Or?
But I agree with that, Emmanuel. I think more examples are needed and better examples are needed to explain these concepts better. So that's definitely something to work on, because I think this is something that needs to be talked about more in the group. So that's definitely an area to improve on.
Any other comment? If there is none, our presentation, our seminar ends here for today. And yeah, you enjoy the rest of your day. And then maybe the postgrad students can remain at the end of the meeting.
Great. Thanks so much, Emmanuel. Thanks, everyone. So, Emmanuel, you'd like to address the postgrads? Yeah.
Yes. Because the thing is, I was from the emails that I've sent, I've had a few people comment that they can't make it for the presentation, like Samisha. And after sending an email, she replied days later, and it was too late. Well, thank you, Prof, that you chipped in on that you're presenting today. Otherwise, that would have been a meeting cancelled. But yeah, my comment just being that if there is anyone having conversed with Prof for one reason or another that they cannot attend, can they please let me know on time? Because in the past week, I couldn't know on time if Samisha was not able to attend anymore. Well, in the next week, we've got Samira presenting for us. I don't know if I can check with her since she's present, if you're able to present next week.
Hi, Emmanuel. Yes, I will present next week.
Okay. Yeah. And yeah, my suggestion was, yeah, if it's maybe, I don't know, I'm here to check with others in terms of individually the people. If the frequency is too soon, my suggestion being maybe to end up